Today we are going to finish our discussion of plane motion of rigid bodies by covering section 16.2. And the topic of 16.2 is constrained motion. So basically, the thought process is to take these very general principles of plane motion and then to look at a particular situation and decide which pieces of that can be eliminated from our analysis based on the predefined direction or magnitude or something of the motion itself. So that is the fundamental idea of where we start. So, like we were saying, most engineering applications are constraints. And some of the examples they give are cranks, connecting rods, and non-slipping wheels. And we've talked about some things like this before, where we've had rods like this, where we have a channel that point B moves through. So we know that point B is constrained to motion in the Y direction, and A is also constrained, so it's constrained to motion in the X direction. And we can use that to simplify our equations. And we've done problems very similar to this, in fact, already. So when we start talking about kinetics rather than kinematics, we talk about the motions with the definite relationships between those components, and we can talk about the acceleration and the acceleration of the mass center, or that inertia vector, as part of the F equals ma, or moments equals I alpha, or ma bar equations. So we also, even though we're talking about kinetics, the force and the causes of motion, we still have access to the kinematic equations if we consider if the acceleration is constant. For example, we can use just the traditional translational and rotational forms of the kinematic equations as well. And the little statement here that may be a little bit new is that we can use that kinematic analysis to yield the acceleration of the mass center in the X direction and the acceleration of the mass center in the Y direction. And then, of course, D'Alembert's principle to get the forces. So if you have a rod like this, you can think about the forces acting upon it as being the normal forces at the points of contact, the pull that's occurring here, and the weight acting from the mass center or the center of gravity, and then considering that max bar and a rotation. So in other words, in this equation, we're considering max and may, in other words, the translational a and y components of the acceleration of the mass center and a rotation. So you can see that there's a lot of stuff, and so using constraints, we can eliminate just a whole bunch of that. Now, another thing that becomes kind of interesting is if we have a non-centroidal rotation. We talked about the fact that the moment of inertia of a body is at a minimum about its mass center or centroid or center of gravity. So if you have a non-centroidal, the principle is generally to think about it as rotating about the mass center and then some sort of a relative rotation or translation in addition to that mass center motion. So here, if we have this potato slab, like we like to work with, this looks pretty oval. It's not very lumpy looking. But for non-centroidal, the motion of the body is constrained to rotate about a fixed axis and does not pass through the mass center. This is a very common situation where you have a point of rotation, and because of the mechanical situation or the fastening situation of that body, you can only rotate about one particular point. Just as an easy example, this would be usually centroidal, but there's a type of a firework that's a pinwheel of different firecrackers or little incendiary devices, and you can pin these to a tree or to some other thing that's not terribly flammable, and then the rotation is going to happen about that point, no matter what. It doesn't matter if 3 of these blew off and the force was in a different place or whatever. If you pinned it to the tree in a different location, if you pinned it over here, ignoring the template on the firework, it's still just going to rotate about this. It's just going to be a lumpier spin. So sometimes, and a lot of times, rotations are decidedly constrained about a point. You have a true pivot point. In a simpler sense, if you have a child's teeter-totter and it's mounted on a bracket in the middle, all of the rotation is going to happen about that. Ferris wheel, anything really, anything that rotates is your tires on your car. You don't get to start rotating on the edge. Everything has a constrained element to it. But if it's not, it's more typical to rotate about a centroidal axis. Usually the pin, more typically, and I'm really having trouble today even thinking of any instances where it's not. Maybe some planetary gear systems in a car or something like this, but I can't really even think of a good example of something common that rotates non-centroidally, because the rotation is always much smoother if it's taken about that centroid. But in the event that it happens, the kinematic relationships we can think about the tangential acceleration and the normal acceleration of the center, and the kinematic relations are used to eliminate those from equations derived from D'Alembert's principle or from the method of dynamic equilibrium, F equals ma. All right, you probably would like to see that. Let me put it back here. So it's just another glance at that one. So if we continue with our discussion then, here we have a balanced disk that is constrained to roll without sliding. All right, so this is, I like the bottom one. There's a good example. But the top disk is definitely rotating. It's constrained to rotate about its center. Okay, so if it's balanced, it's just going to always be rotating about the center. So we can describe the x variables and what that looks like. Then if it rolls with no sliding, the frictional force is going to be less than mu sub s n, meaning that otherwise if we have too much, it's going to it's going to not roll, but it will slide as well. And then we have 3 cases for rolling with sliding and pending, and then rolling and sliding. Now this is kind of an important point, and Logan brought this up in the last class, but basically friction is only going to reach some sort of a maximum value. It's never, even though it has the capacity to be stronger, it's never going to push you backward. It's never going to reverse the reaction, because it's always opposing motion. So what we're saying here is that if you have sliding and pending, every bit of the frictional force available to you is going to be used. But when we go beyond that, we get to kinetic friction instead. So in other words, kinetic friction is generally a lower value, and it's not a steady decline. It's like you're either sliding or you're not. So you either have static friction where everything's gripped up good, or it starts to slide, or it starts to slide, and in that case you have a slippery condition. This is also why if you're driving in the winter and it's very icy outside and you come to a stop for some reason, you're at a stoplight or whatever, and you have to start going again, it's actually quite a bit better to try to move slowly. If you can keep your wheels from spinning, you're not going to lose that static friction potential. Now, that is also very unsatisfying because it takes a long time and it feels like you're slipping anyway. So a lot of people will just put on the gas. Well, there is another advantage not shown in this equation by putting on the gas, which is if you spin, you create friction in the spin itself, and you can generate heat, and you can actually melt a little bit of the surface that you're slipping on. So there's that, and that's actually well, I'm not going to get into that. There's an application for that, but it's hard for me to draw the connection here. But anyway, the basic thing is that in general, from a strictly static and kinetic point of view of friction, if you need more friction, it's better to stay in the static range almost all of the time. Here's a case where we have a disk a semicircle cut out of a circle, and it is asymmetric. So in this case, if we talk about the center of rotation, the mass center is right here at G. It would be here, wouldn't it, if the disk were not cut out. But this absence of material here scoots our center of gravity to a new location. And if we then want to find the properties, the acceleration of that mass center, we can say that it's equal to the acceleration of the center plus the acceleration, the relative acceleration of G with respect to O. And then we can break that piece up into a tangential and a normal component, where tangential, of course, is the rate of change of speed, and the normal is the rate of change of direction. All right, so here we have a little gear train. This is actually pretty symmetric. This is symmetrical, so we're not going to test that idea yet at this point. But basically, we have this gear. We have A, O, B, which is a gear with a bar fastened to the center. Okay, and it is actuated by this gear B. So what that means is that D starts to turn, and that turns the gear A in the opposite direction. So if this is turning counterclockwise, this will start to turn clockwise. And when that happens at this particular instant, we know that it has a clockwise angular velocity of 8 radians per second, and the counterclockwise angular acceleration of 40 radians per second square. And we want to find the tangential force exerted by the gear D and the components in the reaction of the shaft at O. All right, now it's really important to notice whenever you have gears meshing, at the point where the two gears mesh, the forces are going to be equal in magnitude to each other. If they're not equal in magnitude, the gears are going to slip, or one of the teeth is going to slip. So it's a given constraint of a gear-driven problem that, as long as the problem exists, that those forces will be equal in magnitude. So the first thing we do is we break out that second gear, AOB. It's not really a full gear, it's a gear with a bar on it. And we determine, we're going to do the free body diagram. So we have a weight, and we have some kind of a weight of the bar. So we're talking about the weight of the gear. Hang on just one second. I want to take a peek. Yeah, see, they're calling the gear E and the gear D. So just the variables here are a little unclear to me. So the bar is considered B. This gear is gear E. This is gear D. The point of contact is A. And I don't know if they're going to move the point of contact or not. We're going to find out. And then O is the center of the second gear, the driven gear. Okay, so we can go ahead and we can come up with the free body diagram. We need to include the weight of the gear and the weight of the arm or the bar. And then we can say, we can find that I alpha, which is going to be the mk squared. So this is that mass moment of inertia that we talked about, and those are drawn out for you in your textbook. You have examples of those. We've never really dealt much with mass moments of inertia. We've talked about aerial moments of inertia, but when we get into this type of motion, we need to just extrapolate our discussion to mass moments of inertia. Although I would suggest that the extrapolation is not very much. It's just that you use mass instead of part of the shape. And we're not going to go through the derivation. But it works the same way, and k is just a radius of gyration. So in that case, we can come up with that vector, which is going to be in Newton meters. It's interesting to note that Newton meters is also the unit of either energy or torque. So everything kind of fits together in terms of a gear train. Excuse me. All right, so then we're going to take the mass times the acceleration of the center of OA, this in the tangential direction, and we can compute the mass times acceleration by taking mass times a radius. Now, if you take a look at this radius, we're talking about the distance between here and the mass center here, or where that is going to be acting on that arm. Okay, and then we just come out with an expression for this is going to be the tangential component of essentially the inertia vector, and this is the normal component of the inertia vector. And then we come up with something about that rotational property, the I alpha side. And so these are in newtons, and this is in Newton meters. That's what I want to make a point. So this comes out of the force equals mass times acceleration equation. This comes out of the moment equals I alpha equation. All right, so then we have we're just going to take that force, the force times the distance. So that would be a moment. So we have our force, and we have the distance, or the moment arm. We set that equal to the effective moment summation, which is going to be the I alpha and the inertia vector times the moment arm, and the I alpha of the bar. So we have I alpha of the gear, I alpha of the bar, and then mass acceleration of the mass center of the arm. And we can come up with an expression for the force, which is 63 newtons down. Do the same in the x direction. It's a little bit simpler in the x direction, but we come up with a reaction force at point x, which is in the x direction, I should say, and then a reaction force in the y direction. So in that way we can completely analyze that. But these are all centric, so we're not doing non-centroidal stuff. But it just shows you I can take a fairly complex problem, and based on the constraints of the problem, eliminate a lot of the math. There's still quite a bit of stuff going on here that we have to analyze, but it is a little bit more doable because of that constraint. All right, so here we have a sphere. I want to see if I want to work this one, or if there's another one here. This is all centric. I'd really like to find a non-centroidal problem. Oh, here we go. This should work. And these are actually a classical style of problem in dynamics, where we have a cord wrapped around a hub or a wheel. They're like two concentric wheels, but one is inside of the other, or one is smaller than the other. And so we wrap around a cord. And what's going to happen at that point is we're still going to have a center of gravity that's in the middle, but this force is going to be acting differently on where the rotation occurs. So we have a sort of a semi-non-concentric issue going on here. All right, so if we draw the free body diagrams, once again, we have to remember the weight. We have a force from the cord. We have a force from friction. We have a normal force. And we have the inertia vector, and we have I alpha. So this is actually a really good drawing to start out any sort of a rotating problem. To think about the forces equals the mass center acceleration, or the inertia vector, and the rotational piece. So then they just compute that I bar, which is just from your book. Now I'm not going to put anything really complicated or strange. I'll probably either give you I bar for these types of problems, or make it a circle or something very symmetrical. So we'll be able to do that. And then we're assuming that we're rolling without slipping. Once again, that's a big assumption. And but so then we can make a relationship between A bar and alpha. Otherwise, we've got a little bit of translation going on, and it's not really that predictable of a situation. So then we take our summation of moments and set it equal to those effective moments, which is the MA times the radius and the I bar alpha. And we go ahead and we make a solution for the acceleration of the mass center. Then we sum the forces in the x and the y directions, and we come up with values for those as well. Okay. So I want to take a look at this. I like everything there. That's good. Now here, we've talked about without slipping, and if we start slipping, the only difference is that if we're not talking about impending slippage, we're just talking about the fact that we're going to be focused on mu k instead. In other words, the coefficient of kinetic friction, which is going to produce a smaller frictional force, is going to be in effect once we start slipping. And so if you look at the acceleration, if it's slipping, look at the A bar here, which is 2.5, compared to A bar here, which is 1.7. So once it starts slipping, it starts moving much faster, doesn't it? Which once again you can equate to your tires spinning on when they break loose or don't break loose on ice. Right, and so that's just basically. And then I don't know if I like this problem. This is just a constraint, so I'm not going to go through the math. They do this really geometrically, really trigonometrically, but basically we know that point B has to be constrained to this, and we know that point, in other words, it's not vertical or horizontal, but it's definitely constrained in its direction. it's 45 degrees off of the horizontal or off of the vertical, and then direction of A at that moment is 30 degrees. Now the other thing to recognize is that at every single second, those angular relationships are going to change, aren't they? But whatever the direction of B is, B still has to go down that plane, and A is always going to be constrained to be purely horizontal, even though the angle changes. All right? And like I said, they do a pretty geometric solution here, but this is basically what I would like you to keep in mind, is that the acceleration of this point, which is less constrained, is equal to the acceleration of A, which is more constrained, times the acceleration of B with respect to A. So we can think about that as being that rotation. And the other thing is that, see, this is another thing that kind of, we're just doing it right at this 1 second. It's not, this is not really constrained to be a pure rotation about the mass center. That's what I don't really like too much about this problem. Because the constraint is really the horizontal nature of this and the slope method of this. So we know that this velocity is always going to be directed this way, this velocity is always going to be directed that way. But that's the only thing that we know. And that angle is changing everywhere, because if you think about it, if this is the hypotenuse, and this is the opposite side, and that is the adjacent side to this angle, this is getting less all the time, while that's getting higher all the time. The hypotenuse stays the same, but the angular relationship changes as you continue down that path. Literally down that path. All right, so that's a piece of this that I'm not really crazy about. That's why they do a geometric solution as well, trigonometric solution. So, yeah. Anyway, so do you guys have any questions about that? It's kind of a lot. It's easier to do once you start working problem, I would say. So let's take a look. The problems also tend to be a little complicated. So I'm only going to assign probably 2 problems. Okay. Let's see. If I take a look at problem 1676, let's take a look at that one. All right. So if we look at 1676, we have a uniform slender rod right here. And this is a good example, because we have a fixed pivot point, don't we? And the fixed pivot point is not at the center of gravity. So that does make it a non-centroidal. That's a pretty good problem. I kind of like that. That does make it non-centroidal. So in that way, we definitely are going to have to take a look at moving everything to the center. So let me go ahead and draw this out. Get a better piece of paper. Right. Okay. So we have a long, slender rod, and we are pivoted about a fixed point, and that point is defined as point C. And the rod extends above the pivot and below the pivot. And our center of gravity is in this location, and we have a P here, and we're calling that point B. So if we take a look at all of those types of ideas, we then have a length. We are saying the bar is uniform. In other words, the distance below the center of gravity is equal to, I guess this is in front of this. Does it matter? Yeah, it does matter, because otherwise it's going to crash into stuff. There we go. So we have a length L over 2, we have a force P. It tells us that the length of this bar is 900 millimeters. Oops, you can't see that. There we go. That should work, right? So we have a length of the bar of 100 millimeters. And what else do we have here? The mass of the bar is 4 kilograms, and it's suspended from the hinge at C, which we're also told that this distance, we're calling it R bar, which makes sense because if the pivot is here, they're just using R bar because that's the same symbol that you would use in the equations for that moment arm between the two, between the center and the pivot. All right. So we're told that R bar is equal to 225 millimeters. We want to find the angular acceleration of the rod and the components of the reaction at C. In other words, we want to find the force at C in the x direction and the force at C in the y direction. Okay? All right, so if we look at that problem, what do we know? Well, the first thing we know, we have this R bar, so we know that the acceleration of the center is going to equal that R bar times alpha, if we consider that as being that rotation. And for a slender rod, in your textbook, the mass moment of a slender rod is, oh, that's way back there. Let's see. There we go. The mass moment, this is from the back cover of your book. So if you take a look at this, we just basically have this kind of a slender rod, and it says that I sub y, so this direction, and I sub z are both equal to, that would be about the mass center, 1/12 mass length squared. All right, and we have all of that data in our problem. All right, so once we start that, we can set up our equation, and we can say the summation of moments about the point where we are pivoting, which is C, is going to equal the summation of the moments about C, the effective moments. I can get rid of this. And so this force P is creating a moment, and that's going to be clockwise, so it's actually minus, and this distance is L over 2 plus R bar, isn't it? So we're going from here to here, all right? And that's going to equal that mass times the acceleration of the center times the distance, which is the distance from the mass center to point C, which is R bar. Okay. And then the only other thing we really have going on is the rotation, which is our I bar alpha. Okay. So let's go. Did they tell me what P was? 75 newtons. All right, so we get 75 newtons times L over 2, which is 450, plus R bar, which is 225, is equal to the mass of the bar, which is 4 kilograms, times the acceleration of the mass center, right, which at this point is unknown. Force, this is that R bar, which is 225, plus I bar, which we need to calculate. That's 1/12 times 4 kilograms times 900 millimeters squared. Boy, I'm really thinking I want to go to meters instead of millimeters, but what the heck. So we have 900 squared times 4 divided by 12. That number is 270,000, and that's going to be in kilogram millimeters squared. Okay, so finishing that off, we're going to get 270,000 kilogram millimeters squared times that value of alpha. Okay, now we have an A. Did I leave it out? Here's this, 4 times 225 times alpha, or times A bar, sorry. All right, so we have A bar and we have alpha in the same equation. We have a relationship between those two, right? If we look at our mass center and we think about that in terms of the distance to the pivot, we can also say that A bar is going to be equal to R bar times alpha. And so if we substitute one or the other, we can do that and put that in here. And we're going to get 75 times 675 is equal to 4 times 225 times R bar, which is 225 again, times alpha, which is unknown, plus 270,000 times alpha. All right, and then what we have there is a single equation with a single unknown. So we can factor that out. If I take that number, the 270,000, and add to it the coefficient of alpha over here, 4 times 225 times 225 again, that gives me 400. Okay, yeah, so this together, this is 75 times 675 equals 472,500 times alpha, and alpha then is equal to this number, reciprocal of that, times 75 times 675, and that value is 0.107 in units of radians per second. Squared, excuse me. Okay. Yeah, I dropped something. Talk to me. I need to change these into meters. I can't work with that in millimeters. How's that? Does that answer your question?
I was going to ask you where you get the 225 alpha from to substitute A bar.
Yeah. If you look at this, A bar is the vector here, right? The acceleration of the mass center. Well, it's pivoting. All of that is pivoting about C. So,
it's
yeah.
It's kind of like a moment there.
Yes, it's exactly what it is. It's I bar alpha. This is just if you have a pure rotation. If you have in a pure rotation, linear acceleration or translational acceleration is equal to some distance times alpha. So in other words, in any sort of a rotation, if you know the acceleration about some point, the angular acceleration of some point, and then you know the distance between that point and some other point, and you can find the acceleration of the second point in a translational sense based on that. But I have a deeper problem here. I've got newtons and kilograms and millimeters, and that never works for me. I always think it will, and it's never a good idea. So that means that the length is going to be 0.9 meters. And then this is going to be 450. So I'm just going to rewrite this because otherwise I always have this issue. So I'm going to say P, and I'm not really sure. I feel like that should be a negative. But if I do that, my alpha is also, see, I think I get a sign mixed up there if I do that. And I really don't like that. Because my alpha is in this direction as well. It's not turning this way. That's a different picture. So it's going this way. So I'm going to keep everything positive in this. I'm going to just keep everything as being positive in the clockwise direction. And so that way I'm going to eliminate that sign issue as well. All right, so, and since it's plane motion, we can do that. All right, so we have P, which is 75 newtons, times L over 2, which is 0.45, plus R bar, which is 0.225, and those are both in meters, is equal to the mass of the bar, which is 4 kilograms, times the acceleration of the center, which is this distance, r bar, 0.225 meters, times alpha, okay, just to get rid of that variable, plus my I bar, which is going to be 1/12 times 4 times 0.9 squared, which makes me so much happier. So if we do that, we get I bar is 1, see, I didn't even do it right, that's a problem. 0.9 times 0.9 equals times 2 is 1.62. So I don't even know what I have here. This should be 1.62 I bar equals 1.62 kilogram meters squared. Okay, now that just is a much more functional number. All right, so I've got 475, here we go, 75.45, 4.225 alpha, which is A bar, right? And then here we have, but I need that R still in there because this is mass times acceleration. Then I need that R bar again because that's a moment, okay? So I need to multiply that by 0.225 again. And then I have I bar, which is 1.62 kilogram meters squared times alpha. Okay. So then on the left-hand side of the equation, I have 50.625 Newton meters. And over here, I have 4 times 0.225 times 0.225 times alpha. So that's 0.2025 alpha. Let's make sure I have everything there. Yep. Plus 1.62 alpha. And this is in kilograms per meter, kilogram times meter squared. So if I add those two values together, I get 1.8225 alpha, and that's going to be 50.625 Newton meters, and this is in kilogram meters squared. That's something funny with my units. Maybe not. So if I divide both sides by that 1.8225, I just have something wrong with this. My math is not coming out the way I want it to. I may have to work that out. I think now I've got my, I feel like now I have my moment of inertia wrong. Because I have Newton meter per kilogram meter squared. And a Newton per kilogram is, from F equals ma, meter per second squared. Oh, well, at least the units come out correctly, because then my meters squared cancel out, and I'm just left with per second squared, which is a good unit for alpha. But I don't like that. That number's not right. So I have an algebra mistake here, and what I'm going to do is I'm going to go back and work this, and I'll put an addendum onto this lecture so that you'll be able to see the setup is correct, but I have something. I feel like, oh, did I forget? Oh, I forgot. I see what it is. I got it already. Here on I bar, I divided by 2 instead of dividing by 12. So I bar is 1/12 times the mass, which is 4, times the length of the bar, which is 0.9 meters squared. Okay, so let me do this again. 0.9 times 0.9 equals, times 4 equals, divided by 12, is 0.27. I bar is 0.27 kilogram meters squared. Yeah, that's better than this one. That's a big number. And also it looks more like this. So you can see that when I calculated it here, I just had weird decimal places. So this, the mantissa, the number part of this looks much better to me. Okay, so now everything's going to be fine except I bar is 0.27. I already worked out my units. So what that means is over here, this number is going to be 0.2025 plus 0.27, which is 0.4725 alpha. So I divide this by 0.4725. Let's have something funky here. I'm not sure what it is. 1 over answer times 50.625 is 100, yeah, that's all right, 107.1 radians per second squared. All right, that actually looks correct. So all of the work here was correct, but I had I had a conversion error somewhere in my millimeters, and I really should know better. That never works for me. I have to put everything to base units, or I always come out with some weird number of decimal places. Then the next part is I divided by 2 instead of 12. So this is correct. So we don't have to do an addendum. All right, the next part then, we have 2 minutes left, is to find the components of the reaction at C. All right, well, that's where our pivot point is. So if we take a look at C, we're going to have some force at C in the x direction and some force at C in the y direction. Let me see if I can put this up on the... Here, let's just do it like that. All right, there we go. So in the y direction, we have just the reaction at C, the force at C in the y direction, pulling it up. And all we really have is the weight pulling it down, and it's not going anywhere, so that's equal to 0. So the force at C in the y direction is just equal to the weight, which is equal to the mass times gravity, 4 kilograms times 9.81 meters per second squared. So 4 times 9.81 is 39.24 newtons. Okay. Now, on the other one, in the x direction, we have this force at P, which is negative, and we have, the way I've drawn the force at C in the x direction, the force at C in the x direction, okay? But that's going to be equal to mass times acceleration. So we're talking about mass times the acceleration of the mass center, okay? So then we can say the force at C in the x direction is equal to mass times that acceleration plus P. But that acceleration, let me think about this. That acceleration is going to be counterclockwise, or clockwise. And this would be pulling it in the opposite direction. So this is actually going to be a negative right here. Okay? So we're going to subtract those values. In other words, this is going to contribute in one direction, and this is going to contribute in the other direction. All right, so this is 75 newtons that we're pushing with. What is my mass times my acceleration? Well, I know the mass is 4 kilograms, and the acceleration is actually going to be r bar times alpha. So this is 4 times r bar, which is 0.225 meters, kilogram, meter, acceleration, 107.1 radians per second squared, plus 75. Okay, so this is going to be 4 times 0.225 times 107.1, and so this is a negative 96.4, and this would be kilogram meter. Radians is a fundamental unit, so it falls out. So we have kilogram meters per second squared, which is a newton, plus 75 newtons. So in the x direction, this is r bar alpha force C. That's what we're equal to. Force Cx then is equal to, because this is going that way, that's going that way. And so we have 96 plus 75, negative 96 plus 75, which is 21.4 newtons. So the force at C in the x direction is going to be 24 newtons, which makes sense because we have a force going in this direction from the reaction. We have a force going in this direction from the acceleration, and then P is opposing the two of them. All right. See, I have to go back to this directional thing. This is moving to the right. This is moving to the left. So what that means is, way up my sign convention, this is actually moving to the left. In other words, the acceleration is pulling it to the right, P is pushing it to the left, and the reaction is actually holding it back, going to the left. So according to my own convention, if this is negative and this is positive, this is negative. So it all works out as long as I put my signs down, right? Okay, do you guys have any questions about that? One thing that you might feel, I know that this is, there's a lot to pull together, but everything that we're doing, you've already done. I mean, we're just sort of adding more pieces. So when you construct these types of equations, the one thing to remember is that when you do the moments, you still have to think about the directions of the moments, but that the inertia vector makes a moment about the rotational spot, and then we have the I alpha. All right, so these are effective moments. So this is really like, I don't know if it's a new piece exactly, but there are two different components, and they both kind of look, they're kind of rotational. I mean, we're using a bar as a translational acceleration, obviously, but when we create a moment then about that pivot, it has a rotational kind of feel to it, but it's not contained within the I alpha component. It's a different piece of that acceleration. All right. All right, well, that's it for today, gentlemen. What we're going to do then, I'll put up 2 homework problems from section 16.2, and that's it for chapter 16. I've also put your quiz is open. Yeah, your quiz is open, and you probably want to see that. Here we go. There we go. The quiz is open, and I've left it open until Monday, November 4th, if you haven't taken it yet. And then you can submit your work for the quiz right underneath it instead of emailing it to me like we did the first time. And Anthony, I did get yours. Everything looks super. So then we'll start on chapter 17. We'll do 3 lectures on chapter 17, and then the following week I will not be on campus, so you'll have a chance to catch up with everything. So. All right. Well, you guys have a wonderful day, and we will see you Monday for more fun with Chapter 17.